In this demo, I'm going to show you the battery toolbox and how you use this toolbox. So let's start Otii. To use the battery toolbox, you need a battery toolbox license. So you can find the information about the license and buy a license at our homepage on the buy page. So the battery toolbox is this license. So let's start by signing in. And I need to reserve my battery toolbox license. And the battery profiling tool can be found here. So let me explain this battery profiling function here. So this describes how the battery is going to be discharged. And there is a setting here that is the nominal voltage of the battery. All this data I will walk you through. So there is a nominal voltage and there is a 2 level of discharge. So there is a high discharge and a low discharge of the battery. And I'm going to show you how I set this up. And then there's also a setting of when the profile is going to be stopped, when the battery is empty. And you can also add some extra data here. Like in my case, I'm going to discharge a Murata coin cell battery. So the device I'm going to work with now is the generic node sensor edition. It's a LoRa device. And what I'm going to do is I'm going to profile a CR2032 battery for this device. It sounds too small for this, right? So let's see how that works out. So the battery here is the Murata CR2032R. So that means it's the high discharge version of this battery. And it's a good starting point to have the battery datasheet. It's also good to have discussion with your battery manufacturer to get all the settings correct. So this is the battery I'm going to discharge. So looking into the specification, so I have a nominal voltage of 3 volt and a nominal capacity of 200 milliamp hours. And then there's information about how much I can discharge, how high current I can discharge this battery with. So first I need to understand my device, because it's the device that will consume the energy from the battery. So let's start by looking into the current consumption of my generic node device. So let's start by powering up the device. So the coin cell battery is 3 volt. I would like to see the current and the voltage here. So I start the recording, power up my device. So first, I mean, it's a LoRa device, so it will start by to include in my LoRa network here in the office. So let's wait for that to be finished. Yeah, so this is an active phase, so let's just make a new recording. So I will rename this. This was the include phase. Let's wait for the device to do a complete TX and a wait cycle. I'll hide this include phase now. I'm not interested in the include part right now. We'll be focusing on this active period. Okay, so here we can see a full active period. So I stop there. With the battery profiling tool, I can select the different levels of discharge, if it's going to be a constant current discharge, constant power, or a constant resistance. In this case, I will be looking into if it is a constant current or constant power discharge. And I expect it to be a constant power, because I know there is a DC-DC converter involved here. So let's see how that looks like. So if I actually lower the voltage, then I'm expecting the current consumption in this active phase to increase. So let's make a new recording. So this was my 3 volt recording. So here we have one active phase, so let's wait until we have the next active phase so we can compare them. And there we go. So let's stop that recording, call it 2.5 volt. And I would like to move so I can compare the current consumption here. So let's just make a quick move. Let's move the yellow to the right and zoom in a little bit. Yellow will move to the left. Okay, so as expected, you can see that the current consumption went up when the voltage went down. So this is a typical constant power consumption. Let's mark it here. So in 3 volt I had roughly 35 milliamp, and in 2.5 volt roughly 43 milliamp current consumption. So if I then do a calculation, so I had 3 volt, let's focus on the 3 volt recording. So I had 3 volt and 35 milliamp. So 105 milliwatt. Looking at the 2.5 volt, I had 43 roughly. Yeah, so 107. So let's say in this case, if I bring up again, so I know now I would like to have a constant power discharge at 110 milliwatt. So let's now find out the time. How long time will this discharge be at 110 milliwatt? So this is the active phase. So it's 5.6 microwatt hours. So in this high pulse, I would like to consume the same energy as I do here. But since I have this high current, this high power, it will not be this long, more than 2 seconds, because then I will discharge it too much. So I will calculate for how long time I need to have 110 milliwatt, and that was to get 5.6 microwatt hours. So that 5.6 micro, and I divide it with the 110 milliwatt. 110 milliwatt. So this is how many hours so let's convert it. 2 seconds. Okay, so 183 milliseconds. So if I 183 milliseconds. So if I consume 110 milliwatt for 183 milliseconds, then it will correspond to 5.6 microwatt hours. Okay, so I'm done with my high discharge pulse. Let's move over to the low discharge. So if I look into my device here, so I have a very low sleep current, 2.2 microamps in sleep. And also it's worth mentioning the cycle time here. I have a cycle time of roughly 20 seconds. This is only for development purposes. I would like it to be active much more often. What this application really have is perhaps to send one message every hour. So that would mean if I would discharge according to how my device consumes the energy, then the cycle time here should be 1 hour. That would mean 3,599. Yeah, let's skip that. It would be something like this, but I cannot take that long time. Let's see, I can use the battery life estimator tool here to see how long time that really would take. That would be an interesting exercise. So to use this battery life estimator, I need to enter the capacity, and we saw in the datasheet the capacity for my Merata coin cell battery was 200 milliamp hours, and if I mark the active period here, I get that. I can also edit here in this window. And then my sleep here. But as I mentioned, this was only for this evaluation to have this short cycle time. So actually it would be once every hour. So that would be 3,600 seconds minus 2.2 seconds. So let's calculate that. So this would mean a discharge time of roughly 6 years. I don't have time to profile this battery for 6 years, so I needed to shorten this discharge time and to create a more accelerated discharge profile. So as you can see, the lowest discharge current here is 100 microamp, but I mean that will not shorten this to short enough for me. So 2.7 months is still too long for me to wait until I get a complete profile. So I will also shorten my cycle time. So let's see if I do 1 pulse every minute instead. So actually 60 seconds. Now let's have 57.7 to compensate for this. 1.3 months. Yeah, getting there. But I would like to have it even quicker. So let's have twice every minute. 26.2 days. Yeah, that's all right. So if I then have the low discharge for 27.7 seconds. So now I can guess that this discharge will take roughly 26 days. So to use these tools together is very useful here. And then my exit conditions. Coin cell battery is discharged when you reach open circuit voltage of 2 volt. So this setting is that I will stop the profiling if I reach open circuit voltage of 2 volt. It will also be stopped if I reach a cutoff voltage. So here I could enter the cutoff voltage of my device, but I would like to see how my device behaves below that. I would like to have a little bit longer profile. So my device maybe stops at 2 volt, but I will discharge the battery a little bit more. So 1.5 volt I will set here. And I can also choose if I would like to have a limit in the number of iteration between high and low. But in this case, I would like to keep it to the maximum. When I do the discharge, I recommend not to do a recording at the same time, because this discharge data, it will be stored anyway. So there is not really any use of having this auto recording of when I discharge the battery. If I discharge for a very long time, then the system might be slow. For a long recording, I recommend not to have this selected. But to show you how it looks like, I of course will have it doing a recording. And here I can add some data. Yeah, the model was CR2032R from Murata. So now I need to turn off the power of my device and connect the battery instead. So let me do that. So I connect the battery straight into the main terminal of the Otii ARC. Let me just clear up a little bit. And start the profiling. So what it does now, it will do an offset calibration before I start discharging. So now the battery will be discharged according to my setting here. So, and it will continue until I reach the exit condition. And when the exit condition is reached, then it will automatically stop the profiling, and I can then save my battery profile. So the battery profile created in this way can then be used to emulate the battery. So as you can see now, I have 2 cycles here, and it will continue doing like this. I will stop this. As you can see, when it's stopped, you can save the profile. And I will show you how it looks like now when you emulate the battery. So going back to my device, I will connect it again. I close this battery profiling tool. So now I can, with the battery toolbox license, I can emulate the battery. So instead of just being a power box as I was before, I can use all the data from all the batteries profiled. Here is a lot of profiles. All of these are created by the tool, by discharging batteries. So let me pick CR2032 Murata battery. So here is then the data that I got when I discharged the battery. I can now decide where I want to be on the discharge cycle of this battery. Do I want to try my device when it's new, the battery is fresh, or do I want to see the device behavior when I'm running out of power of the battery? The state of charge here, constant or track. Track means that when I consume energy, I will move along the discharge curve here, and constant means that I will stay at this position all the time. I will choose track, and I will choose a brand new battery. So let me apply that. I will keep this window open. As you can see, I'm above 3 volt now. Fully charged coin cell battery is roughly 3.2 volt. So let's start a recording. Turn on the power. So now the device start to be included in the network again. And as you can see now, when the device consumes energy, this use capacity will increase. And you can also see that when there is a pulse, you can also see that the voltage drops, and this is due to the internal resistance of the battery that was collected during the battery profiling. So now I can start play around with seeing how the device behaves with the different state of charge of these batteries. So let's, for example, see how it behaves when I have used 100 milliamp hours from this battery. So as you can see now, the voltage drops, so I have a much lower open circuit voltage and a much higher internal resistance. And the voltage drop for this peak gets deeper and deeper. So let's see if I can find a spot where it is not working anymore. How does it look like when I have used 110 milliamp hours? So now I can start just moving around on this discharge curve to see the behavior of the device. Yeah, looks alright, still working. Let's move even further out. Okay, yeah, this does not look good. So now, somewhere between 110 and 120 milliamp hours, my device will stop functioning. So this is how you work with the battery toolbox to profile both your device, profile then your battery, and then emulate the battery to get more information.